Hey everyone, welcome to the last video for the numerical method stuff for this class. So this video we're going to be talking about the Runge-Kutta fourth order method. And yes, that's how you pronounce their names, at least as far as I'm aware. Runge and Kutta, they're both German, so that's kind of what you get out of it. So we're going to do a brief discussion on this method, what it is and how you get that it's fourth order. We're not actually going to prove it, but the algebra is just awful. But the idea is the same as what we were talking about with our previous methods. So let's go ahead and just start talking about that. So in this video we're talking about the Runge-Kutta fourth order method. And I've seen this written several different ways. You can talk about it as the Runge-Kutta method. I've also vaguely in the past referred to it as like just RK4 Runge-Kutta fourth order method so that you know what it is, what order it is, and how it all works. So basically, this is just a more complicated way of approximating these derivatives. If you look through the book, you can sort of see how it's all put together, right? So your standard Euler method corresponds to just like a right hand or left hand endpoint integration technique. So this is right hand endpoint integration. If you look at improved Euler, this is like the trapezoidal rule for integration. And this method is something like Simpson's rule. And then it uses more points in the interval to try to calculate the integral or to calculate the derivative or integrate these curves, but it gives you a higher order approximation when you're done with it. So you can look in the book on page 468, it has the formulas for this method. And this is, I don't really see the point in writing it out. Basically, it just involves taking third steps up to your interval of h, getting up 4 different constants, and using those 4 to put together to approximate the slope of your function at that point. Now, it's also possible to show that the local error here is h to the 5th. The calculations are basically similar to the ones we did in the Euler's method to show that that was order h squared locally, but the algebra just gets nasty. I mean, so showing that the improved Euler is order h cubed would be pretty nasty algebra as it is. This is about 4 times worse than that. It just gets worse and worse with every step. But the same method, just pushing that through, will show you that this is order h to the 5th locally, which means the global error is order h to the 4th, which means we have our fourth order method. So what does this mean? This means that if I cut my step size in half and I'm using the Runge-Kutta fourth order method, then I would expect my error to be cut down by a factor of 16, or 2 to the 4th. If I cut my error down by 4, I expect it to go down by 4 to the 4th. So it gives you a vast improvement in what your method's going to look like and how close you're going to be to your solution by cutting your step size in half. So it gives you a vast improvement, which is why this method's usually used a lot, because of the improvement it gives you for a small increase in calculations, right? Like I mentioned before, if I cut my step size in half, the computer has to do twice as many calculations. If I'm only getting a half improvement in my error, that's not great. If I'm getting a 16-fold improvement, that might actually be worth it. So the method might look pretty complicated if you look at it in the book or in other sources, but writing code to do this is not too bad. Really, all these methods, you're going to be writing computer programs to do all this for you. I mean, right, you can't have computers on exams. So exams questions are going to have to be pretty specific in what you're supposed to do in order to test this material. But in terms of actually using these methods, you're going to write a computer program and do it for you. And that's just writing a loop and having it do this at every step and just having it do it and do it and do it over and over again until you get to what you want out of the solution. So while it seems pretty complicated, having a computer do this is not too bad. And that's really where the methods come from, is using computers to help you numerically solve ODEs, because we don't have solutions by hand for them. All right, I just wanted to give a little description of the Runge-Kutta fourth order method here. So that's all I really want to talk about for this video and for this section as a whole. We'll be doing problems in class on Monday where we do actually present these sort of methods and write code to do them. So ideally, we'll be in a computer lab, we'll be talking about this, and you will have chances to write these methods and see how they work. So thanks a lot for watching, and I'll see you in the next video.